This video is going to cover the first part of Lesson 1 from the Rotational Motion Unit. This video will just cover some basic definitions and some equations, and then the next video will go into the examples. So with rotational motion is very similar to linear motion as far as the equations that we use. There are a lot of parallels. And so when we talk about linear motion, which was earlier in the year, we were just talking about things moving in a straight line. Now we're talking about what happens when things go and start rotating around a circle or around any kind of axis. So any point that rotates about an axis will go in a circular path. And so here are some of the analogies. When we were in the first unit, we talked about displacement. And sometimes we called that delta x, sometimes we called it d for displacement. Those were our variables in how we talked about displacement. And displacement is basically just going from point A to point B in a straight line. When we talk about angular displacement, we're going to talk about theta, and that is the angle. How far does it travel? Over here in the margin, I'm going to draw a circle. And so however far whatever you're talking about travels, it's going to cover this certain space, and it's going from point A to point B. So similar to how I was going point A to point B with the linear motion, but now it is going in a circular path, and so we call that theta. And we know that the angle on that arc is congruent to the angle at the center of the circle. In the linear unit, in kinematics, we would talk about velocity, which of course we used a v for velocity, and we measured in meters per second, and it's basically speed. Now we're going to talk about angular velocity, and it is back to the circle idea. It's how fast is it traveling on that angle? How fast does it go across that angle? Now, our angular velocity variable is an omega. And it kind of looks like a W, but it is an omega. It's a lowercase omega. And on the next page, I've got one printed out where you can see in a font what it looks like. But it kind of looks like a curvy W. I'm going to turn the page so you can see that omega. Down here on the margin, I have what an omega looks like. See how it's a W? It's just kind of a curvy W. But that is an omega. So that's what that is. But that omega stands for angular velocity. And we measure angular velocity in radians per second. And if you have taken Algebra 2 or pre-calculus, then you know when we're talking about circles, we often talk in radians. And so radians is going to be the unit that we typically use with the angular velocity. Acceleration in the linear world was just an A, and we measured it in meters per second squared, or meters per second, and it's how fast something is speeding up. Angular acceleration is a similar concept. This time we use an alpha. And alpha looks kind of like this, and again I'll show you down here. Here's your alpha. It kind of looks like an A, but it's just a single line. It's just a single, anyway, however you want to make that, but that is an alpha. So just understand when you are talking about that letter, that is an alpha, and it stands for angular acceleration. And so we have an alpha for angular acceleration, and we measure it in radians per second squared. And again, it is how fast something is speeding up. So thinking about a disk. So if this disk, a lot of the questions will say something like, we have a disk and it starts at rest and it speeds up to a certain speed. What is its angular acceleration? And so we're just asking, how fast is it speeding up? Okay, those are some of the basic variables, terms that you need to know for this unit. Let's talk a little bit more in depth about what those mean. When we talk about angular displacement, a couple things that we need to think about. First of all is when we talk about displacement, when we go in the counterclockwise direction, that is the positive direction. When we go in the clockwise direction, that is the negative direction. And again, that is something that you should know from your math classes. And that's the standard that we're going to use. When we talk about angular displacement, it's the difference between its final and initial angles. And so we're basically talking about our change in theta. That's our angular, how much did the angle change? And so that is our final minus our initial would be our change in the angle or the angular displacement. Remember when we were in the kinematics unit, we were talking about the linear things. When we talked about linear, we had a very similar situation. It was just change in x, and it was the final minus the initial for the change in x. By convention, angular values are positive if they are counterclockwise and negative if they are clockwise. That is what I noted over here. The SI unit is the radians, so we are going to be working in radians. Other units of angular displacement are the degree and the revolution. So sometimes some of the problems might talk about degrees, or they might talk about revolutions. And you maybe have heard of revolutions per second, revolutions per minute. That is an angular displacement term. Okay, well, when we are converting between radians and degrees, again, back to your math classes, you should know that a circle has 2 pi radians in it. And so in the unit circle, if you start here and you go all the way around, you have gone 2 pi radians. Whereas if you just go halfway around the circle, that's 180 degrees, and that is pi radians. So 2 pi radians is 360 degrees, which is equal to 1 revolution. If you need to convert between radians and degrees, we can use the conversion 360 degrees over 2 pi radians. Or if you make it a little bit simpler, you could just talk about half of the circle, and that would be 180 degrees over pi radians. If we need to go from degrees to radians, then we just do it the other way. We say that there's 2 pi radians in 360 degrees, or we say there are pi radians in 180 degrees. And so we would just use that to multiply to change over from one unit to another. And so we have an example here. How many degrees are in 4 radians? Well, if we have 4 radians and we want to find out how many degrees we have, then we need to use one of these. I'm going to use the 180 over pi. It's just a lot, since it's a smaller number, it's just easier to do. And when we do this unit conversion, it's helpful to have your units on here so that you realize these radians cancel out. And if you take 4 times 180, that is 720. And if you take 720 divided by pi, you get 229 degrees. So 4 radians is 229 degrees. The next example, how many radians are in 90 degrees? Well, we're going to use a similar setup. We're just going to use the other fraction and multiply it the other way. So we have 90 degrees, and we're going to multiply it by our conversion unit, our conversion rate of pi radians over 180 degrees. So once again, if we have our units up here, we can cancel those units, and so we get 90 pi radians over 180. And 90 pi divided by 180, we can call that pi over 2 in math class. You would just leave that as a pi over 2. Sometimes we might want to go ahead and leave that as a decimal, though, 1.57 radians. It just, it kind of depends on the context, and we'll run across some examples of that as we go along. But that's how you do the conversion rate. Okay, let's talk a little bit more about angular speed. We talked about it up above a little bit, but again, that omega stands for angular speed. It's kind of like velocity. And just like in the linear world, we said that velocity was change in distance over change in time. In the angular world, we're saying that speed is change in theta, or the change in angle over the change in time. And the SI unit is radians per second. Angular acceleration is alpha, is change in velocity over change in time. And again, remember back to the linear, we had that acceleration, linear acceleration, was change in velocity over change in time. And these two were not on the AP sheet, and so they were just things that we need to understand and know. I'm going to have to go back and double check on the AP sheet, but I'm pretty sure that's the same thing with these. These probably are not on your AP sheet, although you can check and see. They just are things that you're just assumed to understand because that is the concept, that's the definition. It's not even, I mean, it is an equation, but it's really the definition of what is angular speed and what is angular acceleration. And once again, the SI unit is radians per second squared. Let's turn the page. Okay, on this page, what I'm trying to do is I'm trying to show you how similar these two sets of equations are. So over in the margin, remember that the delta x is now, as far as rotational goes, we call it delta theta. The velocity is the omega, and the acceleration is the alpha. And so each of these equations are really just the exact same equation. It's just instead of using a v, we're going to use an omega. Instead of using an a, we're going to use an alpha. And that red A, that should be an alpha. Anytime you see an x, we're going to call it theta, and so on. So all of these equations, again, the top three are on your AP sheet. These three are also on your AP sheet. But as far as finding out which one to use and when to use it and what do they mean, we really have already talked about a lot of it because you have it right here. Now, another thing I have in the margin is what happens if we're going in the positive direction and we have positive acceleration. In that case, we are speeding up. And we're speeding up in the positive direction. Same thing, if we're going in the negative direction and we have negative acceleration, we are again speeding up. But this time we're speeding up in the negative direction. If we are going in the positive direction, but we have a negative acceleration, that means we are slowing down, but we're still going in the positive direction. We're just slowing down in the positive direction. And in this case, we are going in the negative direction, but we have positive acceleration. Once again, we are slowing down, but we are doing it in the negative direction. And so just imagine a turntable of some sort. So it's going around and around and around and around. And if it is going, let's say it's going in the positive direction, if we make the acceleration positive, it's going to be speeding up. However, if it's going in the positive direction and we make the acceleration negative, that's going to counteract that. It's going to slow it down, but it's still going to be going in the positive direction for some time. At some point, it will turn around and go the other way, but right now it's just slowing down. So these are parallels again to what we talked about in the linear world. I just want to make sure you understand how they work with circles. In the notes here, it mentions that the variables in the equation of rotational kinematics are sign dependent. So once again, going this way is positive, going this way is negative, and that's what they have here. I'm going to stop the video here and have you work on the ladybug activity and then come back and watch the second video for the examples.